これでレコードが始まる。これでよろしいですか。じゃあこれでずっと。お願いします。すみません。
なんか飛べますよね、はい。
どうですか。2月1日、ソーラスパターン研究会です。はい、小野先生。どうぞお願いします。
今日は新年度じゃない新年第1回の研究会ですが、今日はチャンさんにもご一緒いただいてありがとうございます。不安のある名前の書き方はヨーロッパ式ですか。チャン・ユンチンと言うんだけど、書くときはユンチン、チャン。これが普通ですか。あ、そうですか。いつもの通り、研究会で、お気軽に。
日田先生、何か。
チャンスの話。
どういう順番にいたしますか。
紹介。
お願いします。はい、
それでは今日最初話をさせていただくチャンスさんを紹介いたします。現在、まもなくドクターを取るはずなんですが、8月に台湾の高尾大学の数学科の学生でいます。学生といっても私のですね、非常に親しくしている友人のリー君で YJ リーっていうのがいまして、彼は台湾でのホワイトノイズ解析のリーダーなんですけども、そのお弟子さんなんです。で、去年ですね、年度で言いますと去年になりますけども、名古屋の何学院だかな、名古屋学院の日本語の研修生として来てましてですね。でさっき彼の先生の YJD さんと私たちが非常に交流を深めていることを知ってて、時々名古屋大学へ来てくれました。土曜日とかそれから放課後なんかは来て勉強してましたけども、でそれに弾みがついてこの1月の初めからですね、短期間ではありますけども文部省の留学生みたいな格好で派遣されてきたんですけども、留学生といっても自分で希望してきたわけでありまして、オフィシャルには休みではなくて出張で来てるわけですけども、経済的なサポートをなして、実はプライベートに来てるわけですけども、非常によく勉強してまして、師匠のYJD さんのやってるような方向をさらに最近のですね、ホワイトノイズ解析の中心的な話題である新しいノイズ、これはCC さんが少し前に言い出したりしてファッショナブルなトピックに今なりつつあるんですけども、それについて研究をしておりまして、私も少しエンカレッジをしている関係でありまして、で先日のヤンゴンでの国際学会にコントリビュート・ザ・ペーパーの方で推薦されまして、向こうで話をしておりますが、そんなわけで非常にアクティブにやっておりまして、内容がですね、こ こでSNS の言語の問題でいろいろ研究が続いているその基礎になる数学的な理論と非常に深い関係がありますので、その面で一応は一遍最近彼女のやっていることを報告してもらおうと思っております。よろしくお願いします。
どうぞ。映しますか？パワーポイントで映しますか？わかりました。ちょっとお待ちくださいね。はい。ちょっとお待ちくださいね。どうでしょうか。こっち2番ね、これの絵。元から伝えませんでした。はい。
ああ、そうですね。1の方ですか。こっちは曲がって。
かなり曲がってますね。これは、どっちですか？これが一番大きいか。
そうなんです。ちょっと考えます。
いやいや、これを下げる。
もうちょっとだけですね。
どっち？こっち？
はいはい、それでいいです。
こっち？
そうですね。いや逆じゃないです。
こっち？
違います。こんなもんですよ。
英語でやる、日本語でやりますか？英語でやる。1年間日本語の研修をしたんですけども、こっちの方はものにならなくて、やってる数学の方がものになると思う。そんなわけで、英語でやるそうですから。
はい。お願いします。どうぞ。
Thank you for Kuma Sensei or Yamaguchi Sensei invitation. So it's my first time to come here. It's my pleasure to take this report. And today,
Speak loudly.
Today my topic is multiplicity of linear system based on space noise. First, I will give some introduction. Our work is based on the noise, which is a system realized independent variable with continuous parameter. We can say t, the time, or the lambda, the space. There are the three typical cases. One is a time parameter, time-dependent Gaussian case, and the Poisson case. Gaussian case is p dot t, and the Poisson case is p dot t. And another is space or intensity. We call it p dash lambda. I'm going to discuss about the function p dash lambda. It's starting from the linear function. And we are interested in the random system that are expressed as linear function of a new noise depending on the space parameter, taking place of the time t for a stochastic process. We've been motivated by the decomposition of the Levy process, where we claim that intensity of Poisson process discriminate their type. We then take the span of lattice type distribution in order to discriminate it. As a result, we are need to consider linear system and naturally to consider the multiplicity. So the multiplicity is related to the span of the lattice distribution. So we know that the multiplicity is well known for the second order process in the Gaussian case. We'll give the definition, which is standard extension to the case the L2 node cannot use it. It's the Hilbert space technology. It's not application. So we observe in another way. So we can give an observation of the linear system of the new noise from the viewpoint of dependent stochastic system. Now first we will introduce the space noise p dash lambda. Start with the Poisson process pt lambda, and t is go through the whole real line, and the lambda is from 0 to infinity, and the p0 lambda equal to 0. For the pt lambda, the convergence of a pt lambda is limit in distribution. It's also say limit in node. Since we don't have the L2 node topology, as I just mentioned about, so we consider the characteristic functional phi zeta, and the cosine zeta equal to a log phi zeta. The term is lambda t e to the I zeta minus 1. It's easy to see that the lambda and t, they have a relationship. We call it a dual relationship. In the one-dimensional, actually it's the inner product. But even though lambda and t, they are dual pair, but lambda, the range of lambda and the range of t is different. One is through all line, and another is half space. We may consider the time t. If we consider the time t, we give a shift from t to t plus h, and use the dilation to consider about the lambda. From 1 lambda to a lambda, the a is greater than 0. When we come to the Poisson noise p dot 1 t1, we can discuss the function of p dot t and study analysis using the L2 nodes method. So we can do the same similar manner in the Gaussian case. While we want to consider about p dash 1 lambda, it can abbreviation to be p dash lambda. This is another noise. We can say it's space noise. It came from the Levy's 1934 work. As we can come to think about the stochastic pt lambda, the p dash lambda is independent at every lambda from the Gill fund. So we can first to observe the integral. Actually, it's not integral, it's polynomial. From the summable series, we can try to compute its characteristic functional. We say it is phi z dot. The phi z dot can write is in this kind of term. First is expectation, and we can write the summation inside. But because it's independent, we can take the summation tool out to be the product of expectation. So finally, we will get the term. Is one expectation and integral. For all z dot, it's like this term. So we will give a theory. If the measurable lambda, f lambda, the measurable function f lambda, if it's integral on 0 to infinity, then the integral will exist. And also the characteristic function also exists. And the characteristic function phi z dot, it will follow the Bochner-Minus theory. That is to say, it will be positive definite. So since we have known the integral will exist, and so it's finite, so we can guarantee the characteristic functional will exist. And in the corollary, what we just mentioned about the characteristic functional, it has another term, seek C. The seek C also followed by the Bochner-Minus theory. And next, what we are in mind is about the space parameter lambda. And lambda is correspondent to the intensity of a Poisson process. And we say the lambda discriminates the type of the distribution of Poisson type. Although the term lambda, we know it's very significant, but it cannot be visualized. It's mere night. So we must introduce the variable u. It's correspondent to the jump of Poisson process. All we can say is a span of lattice type distribution, and we shall determine the uj equal to uj lambda. And in my previous paper, I suppose that u and lambda is one-to-one response, one-to-one isomorphic. But now to consider it's more complicated, so we need to define the uj equal to uj lambda. So how to define the uj equal to uj lambda is very closely related to determine how we can determine the multiplicity, and we will show you later. So first, what I say a lot about. So we can say, see the very easy example, two examples. First example is come from the Professor CC. She said the xt this process, it can be write as p1 plus alpha p2. And when alpha is irrational, it can be c. The multiplicity is 2. Yeah. And another is from the stable process. If we consider a stable process, the green one and the red one, it can be separated into two parts by the jump u greater than 0 and u less than 0. So we should define the integral. In reality, the integral y lambda is a linear function. Where y lambda is a linear process of lambda, which is a linear polynomial in p dash mu under some assumption on f lambda mu. As we come to the double in multiplicity, the linear system could be classified by the type using a phi group. And the single class could be investigated by the change lambda 0 to lambda 0 et du. So we will introduce invariance under the group action. The group action is the fine group. So our linear correlated system can be parameterized by the u bigger than 0. So that it's natural to consider the action due to the transformation group acting on u. First off, we take the dilation from u to the AU. And in case we will introduce tau s, the action tau s is from u to ESU. And it will satisfy a property that tau s product tau t can be tau s plus t. We then come to the action on the intensity measure, so we can see the transformation. And it just can give the proposition. If the intensity measure of the linear correlated system is tau s invariable, like what we just see, then it's of the form cu beta du. So if under the condition, we will see the tau s, if we take the action on the lambda u d mu, so we can see the characteristic function, just change the variable, use the mu equal to ESU, so we can see the change in variable. So it also guarantees the Poisson process also remain a Poisson process. So namely, the intensity change from the lambda u es to the lambda mu e minus s. Also, the distribution still remain be the Poisson type. A Poisson distribution might be considered to be a simpler compared to the Gaussian distribution, but in some cases, may not so, but quite. Note that the characteristic by the two parameters, the intensity and the scale. It's known from what in my introduction, the time space is Gaussian case and a Poisson case, and the t goes through from the O line, and we can take the shift from t to t plus h. And the second is the space parameter p dash lambda, and we only do the dilation to the p dash lambda. So we should discuss the noise with the space parameter. It can establish the basic noise depending on the space parameter according to the law of small probability. It's in the standard noise, total noise. So we will introduce some Professor Cc's approach, and we try to give two definitions of multiplicity. So when we come to the lattice type distribution, it could be considered to characteristic by the semi-invariant. The semi-invariant is like a summation. So the Cauchy-Zeta has this form. We have the Cauchy function, and the Cauchy-Zeta equal to the phi zeta take log. So the phi is the characteristic function. If the expansion has this form, and the Cauchy 0 equal to 0 is possible, then the semi-invariant, it will characteristic the lattice type distribution. In Poisson case, the kappa n, in the summation we have the kappa n. And the kappa n in Poisson case, the kappa n always be constant lambda. Then the generating function of the Poisson system is has lambda product e to the z dot t minus 1. But the minus 1 is also contribute to the kappa 0. Therefore, we take the lambda et to the representation, and we modify it to be lambda etu. And u is what we know is span of lattice distribution. And finally, we take the lambda tu to make the group action. Like we just said, find a transformation. G is equal to AB01. So from T to GT, we can do it action. And when case 1, A is greater than 0, then the time scale change. And when A equal to 1, we can see the form is the lambda EBU product lambda, product ETU. And in other words, the intensity change from lambda to lambda EBU it also maintain the Poisson system. Coming back to a fine group, we can restrict our attention to the shift. Say only the action on B. So we focus on the action on B. We may repeat such operation as many times as we wish by changing the amount of the shift, by choice the different view. We then come to the observation of the lambda intensity, when the scale A can be fixed to be the 1. Now letting the variable B can be variable, so the expressed lambda EBU has always the positive function. So we come to the theory from the Professor CC. She said the general Poisson distribution and the fine transformation, it can generate all the possible Poisson noise. So now we will give two definitions in the multiplicity. The first one is, suppose the linear system Y lambda, it can be separated into two parts, like what we see in the graph. The example 2, we have the lambda, Y1 lambda and Y2 lambda, and it can be satisfied the two conditions. If Y1 and Y2 are independent non-trivial linear system, and the 2 is if the delta Y1 is equal to 1 and delta Y2 is equal to 0 for any non-empty interval, then Y1 is said to be the multiplicity is not less than 2. And second, we can see the definition 2. If Y has the multiplicity less than 2, not less than 2 at each component, so Y1 lambda and Y2 lambda cannot be decomposed so that the multiplicity not less than 2. Then the Y lambda has the unit multiplicity. So by just the action, a fine group action on T, we will have this following theory. When we choose the side of the view, we can define a double multiplicity. So some expression is start with the Y lambda. We fix lambda equal to 1. We can correspond to the Y product ETU, and action is a fine group action to T to the standard Poisson. We have the Y plus and Y minus according to the jump U respectively. So we can say the Y lambda is equal to Y plus plus the Y minus. So from YU it also have the same phenomena. So we can see the Y plus and Y minus can be discriminate. So this implies that the continuous multiplicity is equal to 2. That is, we obtain a linear system with the double continuous multiplicity. So we will come to the conclusion is the double multiplicity must be positive. So